Morning, folks. So we're going to get to the question real quick here. But before we do that, you guys like balloons?
Yeah.
Good. Have you ever encountered a balloon that was hurt? I have a couple of times, as you can probably imagine. So how do you help to fix a balloon that is hurt? What do you do? You helium.
Oh my God.
Heard a couple chuckles, and that's what I'm going for. Okay. On a more serious note, why do you suppose it is that I hate Russian dolls? They're just so full of themselves.
Oh. Oh, okay.
Because they're inside each other.
That's okay.
Two strong ones today?
That's funny.
All right. Let's take a quick look at the question. We'll be doing an example of this after we go through the homework together. So you throw an object straight up, explain how you can find its maximum height using only a stopwatch. Obviously, you would time it. Any thoughts on which equation you would use? You want to find its maximum height. I'll get those equations written down. Whoa. So if you're given information about time and you're looking for maximum height, can you narrow down? Let's start by picking which equations we would not use. So which equation would we not use if we're given information about time and we're looking for vertical height? First and fourth. These two are not going to be useful at all because this is a horizontal equation. So we're not looking for horizontal distance, we're looking for vertical. So that one's out. This one is, bless you.
Sorry.
That's okay. This one is out too. Why is this out? No time. Without time, it's not going to be useful. So we're down to these two. So if I'm looking at what remains here, I'm looking at this one, and this one does not have any information for me on vertical height, but it does have time. This one has both vertical height and time. So most likely I'll be using this, but you're still kind of wondering, maybe this would be useful in some way. So here's the thing. If you've got an object and you time it all the way up and all the way down, it's going to be kind of hard to figure out how high up that object is. Because, I mean, your final height would be 0. Your original height would be 0. Original velocity, you're not quite sure what that is. But if we have the information about time, it could help us a little bit. And this is kind of an interesting scenario. Any thoughts on how we would approach a problem like this? That's okay. This is a tough one. And that's the reason we're going over it. So here's the thing, and this is something you got to make sure you keep in mind. When an object is going up and coming down, it takes the exact same amount of time to go up as it does to come back down. So what that means is if you time an object from the time you toss it up until the time you catch it again, all you got to do is cut that time in half, and then it's as though you're timing it from the top of its absolute path. And then all of a sudden you have a problem where it's like just dropping something from rest. So again, it takes the same amount of time to go up as it does to come back down. So if you take that total time, you cut it in half, then essentially you have a problem where you're just timing it from the top of its height to the very bottom. So what that means then is that we can use this equation in order to solve for that height. Because, final height is going to be 0. Original height is what we're looking for. And this would then be the height at the very top. So, original velocity, at the very top of its path, it has an original velocity of 0. So that goes away. We've got 1/2 AT squared. And so then if I want to solve for that original height, negative 1/2 AT squared. 1/2 times negative 9.8 is negative 4.9. Negative 4.9 times that negative is equal to a positive. So you get a nice little beautiful equation that you can use to calculate the total maximum height that your object has. And just to make sure I'm perfectly clear, let me just draw this for you. Let's say you throw the object up, it reaches a maximum height, and then it comes back down. If this entire path is, we'll say, 6 seconds, then what we're going to do is we're going to take this, divide it by 2, that gives us 3 seconds, and this is what goes in for your time. Because if it takes 3 seconds to go up, and 3 seconds to go down, then basically what we're doing is we're figuring out the problem from here on down. So it's as though this kind of doesn't even exist. So at that max height, the original velocity would be 0, which is why this is 0. And then that 3 seconds is how long it takes to get down to the ground, and that's what goes right there. Questions on this? So it's kind of a little workaround to this whole problem. All you got to do is divide the total time by 2, plug it into this simple little equation, and you're good to go. Questions on this? Okay, so let's go ahead and take a look at worksheet number 2. This should go pretty quick, I think. So the motion maps for 1A, basically what you're doing for this is they want you to put both motion maps on the same dots. So, horizontally, the speed of your object is not going to change, because after it rolls off the table, there are no horizontal forces acting. So it might look something like this. Your arrows would be the same length. Now vertically, the object is speeding up because there's gravity yanking it down. So vertically, your arrows are going to grow. And that's all I'm looking for 1A. So again, all that's happening here is you've got a constant horizontal motion after the ball leaves the table, but it's picking up speed vertically, and that's what gives it that arc type shape. It doesn't go that way because it's slowing down horizontally. That's kind of a common misconception. Horizontally, it has the same speed the whole time, but it's picking up speed vertically. That kind of gives it the illusion of slowing down, but it really isn't. So that's 1A. 1B, sketch force diagrams. I don't think I really need to draw these. You got gravity down, you got normal force up while it's on the table. When it's off the table, what do you have? Gravity, and that's all there is to it. Letter C, determine how far away from the table that the marble lands. So this is the one that is just going to take a little bit of doing. So we're given the height of the table, and we're given the velocity to the right. So it's 1.5 meters off the ground, and we know that it leaves the table going a speed of 10 meters per second. This is about 20 miles an hour, so that little marble is moving pretty quick. And it leaves the table, eventually it hits the ground. Question is, what is that distance? So, we're going to be solving this in the same way that we solved it yesterday and in the practice problems the day before. We're looking for horizontal distance, so let's just go straight to the horizontal distance equation. X equals vt. Now I know my velocity, that's 10, but I don't know my time. So in order to go anywhere and finish the problem, I have to solve for t. So I can do that using this equation right here. We're going to make a lot of use out of this equation. So if I'm looking at this equation and I want to solve for time, I got to make sure I know what all the other letters are. As long as I know all of them, then I'm good to go on this. So what's my final height? Yep. What's my original height? Very good. What's my original velocity? 0? Didn't I just write down that it's 10? Yeah. So this is a vertical equation, which means this needs to be a vertical original velocity. And because it's just rolling horizontally, there is no original vertical velocity. So this answer is going to be 0 right here. So then we've got 1/2 at squared. Acceleration, of course, is negative 9.8. And now it's just a little math problem that we got to solve for t. So I'll shift this all over to the left to make it positive. 1/2 times negative 9.8 is negative 4.9. And when we shift that over, that makes it positive. And then we can solve for t. Divide both sides by 4.9. And how do we get rid of this square? Square root, both sides. So there's your square root. That goes away. And when you do that math, you should end up with 0.553 seconds. And so then you just take your time and you plug that in for t. Of course, velocity is 10, and your final answer should be 5.53 meters. That's number 1. Questions on this? Okay. Number 2 is like the exact same problem. The only difference is you've got a different height. Now it's 3 meters high. So the motion map's going to look the same. Force diagrams are going to look the same. Letter C you do the exact same way, just with a different height. If you use that new height, you should get a time of 0.782 seconds. And your total distance should be 7.82 meters then. So, in terms of letter D, what effect did doubling the rail's height have on the horizontal range of the marble? For that, if you went through the mathematics of it, you would find that it increased by a factor of x to a square root of x. You don't have to know this, but if you really, really like math, and you got down to the equation of it, it increased by this factor right here. So, in terms of that then, other things that would have affected the marble's range, that would be the horizontal velocity, it would be the height of the table, If we would take friction into account, then the friction of the table would be under consideration. Same with air resistance. But in the beginning, remember, it says those things are negligible, so we can ignore them. Other questions on the worksheet? Sounds good. I'll come around and get that from you.